Ready? Let's roll. Okay. Good morning, good afternoon, and good evening. Welcome you again to this World River and Delta System Source to Sink webinar series. And today we invite Professor Bernhard Peucker-Ehrenbrink and come here to talk about the Mississippi River in organic water chemistry. So before I introduce Bernhard, and is that true? In the German also said Bernhard?
That's correct.
Yeah, okay, so American good. Okay, so next week we have Emily. She was a PhD student, a former PhD student of New Jersey, maybe know him, and come here talk about the Papua New Guinea, the Fly River, the sediment routing in the Gulf of Papua during the last sea level cycle. And also next Friday, we have Uchida University Dr. Francis come here talk about the tracing land, sea, soil, organic carbon transport, and have a couple study of small watershed upreach of Amazon in Peru and Godavari in India, and this creek in UK. So there's couple case studies. So please mark your calendar. So Bernhard and is a senior scientist in Woods Hole, a very famous oceanography institute. Actually, he is still the department head in the marine chemistry and geochemistry. And as you can see here, he originally from Germany and get the I try to see the master, over there, and come here as he's a postdoc at Woods Hole in 1994-96, then stay there until now as the senior scientist and the chair over since 2017. So Bernhard is famous as he initiated the global river observation network, but focused on isotope geochemistry of this global river observatory. So today he will pick up a Mississippi River. Hopefully, if we have time, he can introduce a little bit of that global river observatory platform. Okay, Bernhard, now I'll give the floor to you. Please share your screen and put a presentation mode.
Thank you for the introduction, Paul. Just make sure that this is properly set up. So this is a lottery ticket, and the winning number is 514-628, which is your best bet of when in the springtime the Yukon River, the ice on the Yukon River breaks up in front of Dawson City. And this is an annual competition. The way the ice breakup is being determined is that the community puts a tripod out on the frozen river that acts as an ice road in the wintertime. And this tripod is connected via a line to a community center and connected to a clock. And when the ice starts to move, the tripod moves, rips on this cord, triggers the clock to stop, and that's how the community knows to the minute when the ice starts moving in Dawson on the Yukon River. And this started back in 1896. So this has been going on for 125 years. And it's one of those beautiful, long-lasting records that we have on rivers. Of course, this is just a visual observation. But if you look at this record over the last 125 years, what you notice is that there's a trend. There's a lot of variability, but there's a trend towards an earlier ice breakup by about 2 weeks in the last 125 years. And that is believed to be connected to the general climate change in the northern latitudes. Now, wouldn't it be great to have records like that for many more rivers, and not just visual ice breakup, which is a single event a year, but because these systems are so dynamic, have time series observations on the physical and chemical and biological state of rivers.
You know, Bernhard, the Japanese cherry also blossom at least 2 weeks earlier. You know, the news just showed. That should be something interesting to get.
There are a lot of land records that you know, indicate similar earlier events happening now worldwide, I think. So I want to bring you from the Yukon River, where we have this long physical record, to the Mississippi River, where we have another beautiful record of river chemistry. This talk is not about river sediments. So if you're interested in sediments, now is a great time to log off. This is going to be entirely on water chemistry. But I'm hoping to make it entertaining for you. So this is our network of large rivers that we've been studying for, well, in the Arctic for now almost 20 years, for many of the other rivers for at least a decade. And we are trying to continue this into the future. So let me familiarize you with the Mississippi River. It's a dominant river basin in North America. It's of course heavily modified. You can see the farmland here in green, large cities highlighted in red, and then of course the routing network down to the coast near New Orleans and the Berkfoot Delta affecting the northern Gulf of Mexico. There are big tributary basins here that I will be touching upon in this talk. Of course, the upper Mississippi here, I'll highlight that in green. The Missouri River, which is the significant basin, also the source of a lot of sediment flux in the basin. Then on the eastern side, the Ohio River. On the western side, the Arkansas. I do highlight the red because it is connected, although it's no longer really connected to the main stem. And I'll come back to that towards the end of the talk. And then, of course, the lower Mississippi itself. Our observatory is located in New Orleans. And just to give you an idea of where we are located, so this is downtown New Orleans. This is the Audubon Park and Zoo. And right here in front of the zoo is a dock that reaches out into the Mississippi River. It's a floating dock. It is connected to power. And the Audubon Society allowed us to mount a river observatory on that platform. So the observatory itself, it's currently no longer functioning. We are trying to replace it with a more modern version. Is situated on a sled, can be lowered into the water column, and it sits at 3 meter depth. And because it's floating, it's always at the same depth. Over the years, there has been sampling here, regularly sampling about once a month. But in 2015 and 2016, we had a very intense campaign where students from Tulane University and the Water Institute in Baton Rouge helped us sample the river at high temporal resolution. Shelley Moe at Tulane University coordinated this. Amanda Cuesta, Emily Norris, and Rebecca Wong were the students collecting water samples here, making observations. And then I had an undergraduate summer student fellow at Woods Hole, Stephanie Johnson from St. John's University, who worked up a lot of the chemical data on these samples. So this is the record. As you can see, it stretches from 2015 into 2016. The discharge is here given in cubic feet a second. I apologize for not using SI units. This is USGS tradition, and they haven't changed, although the US signed the convention back in the 70s. In red, you see the individual sample points. So this is 161 samples over a little over a year. So very intense sampling. Almost every second day a sample was taken. Now I'm going to show you this record and then some related records just to familiarize you with the water chemistry. And I'm going to focus only on the major cations today. So calcium, magnesium, and sodium. I'm going to mention potassium, but potassium is typically a minor component of these major ions. And these should be familiar to everyone because this is typical, at least in Europe and the US, to publish water quality data on the back of drinking bottles, for instance. So this is the data that I'm going to show you today. If you want to ask me for additional information on these water samples, we can do that during the discussion. And the way I'm going to show you this data is in a binary plot where I'm plotting molar ratios. So on the y-axis, the magnesium to sodium concentration ratio in moles, and on the x-axis, the calcium to sodium ratio. So both are have the sodium in the denominator, which means that mixing lines in these diagrams are straight lines. And this is a broad scale, a logarithmic scale over many orders of magnitude. I'm showing you this just to indicate where water running off from single lithologies would plot. So if you have water draining karst regions, limestone, these waters would plot here at fairly high magnesium and calcium concentrations relative to sodium. So very high magnesium, sodium, and calcium sodium ratios. On the other end of the spectrum sits seawater, obviously dominated by sodium, with relatively low magnesium and calcium to sodium ratios. Runoff from terrains dominated by basalt or granite, they plot somewhere intermediate here. And then, of course, if you're draining water coming from salt deposits, they plot here. So this is sort of the mixing diagram that you should have in mind. Now, in the following, I'm going to limit the scale of the diagram to this red shaded area here. So we're cutting out the basalt section, the limestone section, and I'm switching to a linear scale. And I do that to show you the variability in the Mississippi River. So if we're looking at these large tributary basins, the upper Mississippi here, this point, this data point, this data point, and this data point, shows you enormous variability over the year. So this is a very heterogeneous basin with very heterogeneous runoff. We look at these the easternmost large tributary, the Ohio, sits in the middle, much better defined, less variability. The Missouri sits towards even lower magnesium, sodium, and calcium sodium ratios, so more dominated by sodium. And then the Arkansas and the Red River are even more dominated by sodium rich runoff. So low magnesium, sodium, calcium, sodium composition. This here is our record for this year of intense sampling in New Orleans, 2015-2016. And what you see is a quasi-linear array that points in the direction of the limestone end member, but sits right in the middle of the basalt, granite, sort of silicate rock end member, some pointing towards the seawater end. And you can see that there is some relationship, some systematic with discharge. So at low discharge, the composition sits down here. At higher discharge, it moves up. So over the course of the year, the river kind of follows these trajectories up and down depending on discharge in the basin, which is essentially a function of which parts of the basins are being drained. This is not a single event. I want to show you that in another data set from 2003-2004, which was sampled by Franco Marcantonio while he was on the faculty in New Orleans. These are the yellow data points, and he sent me splits of his samples, and you can see that these essentially follow the same systematic, this linear trend, kind of a mixture between silicate end member with a carbonate end member all the way up here to the upper right. Now, luckily, the USGS has been very active in this basin. They not only have or had observing stations, real-time observing stations, but they also have a long-term sampling station at St. Francisville, which is a record that goes back to the 60s. Actually, the earliest data are from the late 50s, but not for the chemicals that I'm interested in. So I'm going to show you the record that the USGS has amassed at that station. This is not quite monthly. There are some years that have been sampled monthly, but others that have been sampled maybe 6 times a year. So it's not at the resolution that we had in 2015, 2016, but overall it's a very rich record. And these black data points here are the data for the St. Francisville USGS station. You can see on top of that in red again our record from 2016, 2015, and then in yellow the 2003-2004 record also in New Orleans. So let me dive into this record a little bit more deeply to pick it apart. What I'm showing you now are pure concentrations for the St. Francisville record. So not ratios, but truly concentrations of magnesium, sodium, and calcium. So the individual contributing elements to the ratio plot that I just showed you. Because whenever we have variation in ratios, the question is which of these elements is really determining change in that ratio. Is it the sodium or the magnesium or the calcium relative to the sodium? So that's what we are looking here. And these are annual means. So the top line is calcium. You see this did not change significantly over the last 50, almost 60 years. The sodium in red shows a slight upward trajectory. And the magnesium shows a more prominent, better defined upward trajectory. Again, these are concentrations only, annual means. We look at the ratios, again, the molar ratios. We see that the calcium sodium over the decades has slightly gone down. Correlation isn't great, but there's a slight trend towards lower calcium sodium ratios. And if you look at the magnesium sodium, you see the better defined slight increase in the ratios. Now let's look at this plotted relative to discharge. And what you see is that both of these records increase with discharge. So the calcium sodium has a pretty significant increase with increasing discharge. And the magnesium sodium has also an increase, although less pronounced with increasing discharge, which tells you right away, because of this here, where one goes down, one goes up, whereas correlated to discharge, both go up, that the overall record cannot be entirely driven by changes in discharge over time. So let's dig in a little bit deeper and calculate annual means determined by the LOTUS program for the years 1964 to 2015 for the St. Francisville record. This is the scatter shot that you're observing. This gets more interesting if we connect the years by lines. What we will find is that we are starting here in 1956 and slowly follow this line, this trend, with significant variations along this limestone silicate end member mixing line, up and down depending on the hydrologic conditions. Overall, we observe 2 trends. We observe trends in this direction here, lower left to upper right, and we are observing a trend towards slightly higher magnesium sodium ratios over time. The other thing that is worthwhile is that the flood years here in the Mississippi River. So 1993 is known as the Great Flood. 1983 is known as the flood on the lower Mississippi. 1979 is known as the Easter flood, and 1973 is the third biggest flood event on the Mississippi River. Of course, the biggest event of them all is 1927, but we don't have a record for that. At least I haven't found one yet. So we see that these flood years are plotting here in the upper right. The drought years are plotting in the lower left, and I'll come back to that a little later. There's no data for 1978 for some reason. All right, so how can we make sense of this trend, and how can we extend this trend back in time? So I've been looking intensely for records that predate 1963, predate the San Francisco record. And there's an interesting paper by Frank Wigglesworth Clark from 1927, US Geological Survey, that contains data that goes back in time. There's actually a time series for a year in 1905, 1906 on the lower Mississippi in New Orleans. And what they did that year is someone went out every day with a boat to the middle of the river, took a sample at about 1 meter depth, brought it back on shore, mixed the individual samples for 1 week together to create a composite, and then analyze that composite. So in this data table, we have data for calcium, magnesium, and unfortunately, the combined sodium and potassium concentration, where sodium is always the main contributor because potassium is such a minor contribution. But I need to point this out. And we have that for over a year. So a really great time series record for 1 year back in 1905, 1906. How can we make sense of this record? So let's look at what actually happened here. This is a paper in Science from 1905 by C.H. Stone, who wrote in that paper that he was unable to find any publication of recent and complete analysis of the Mississippi River. So he was instrumental in getting this 1 year time series started because apparently there is no previous analysis of the Mississippi River. So this may be the first ever chemical analysis of the Mississippi River. Also, pointing out sodium and potassium is a combined analysis. So it's worthwhile to look into how these analyses were actually done. And this was, of course, done in the years and decades before modern analytical tools became available. So our own data are all ICP mass spectrometry analysis, as are the data for the 2003-2004 time series. The Mississippi, the USGS work in St. Francisville has some ICP, but also optical spectrometry, but essentially modern analytical technology. What happens for this data in 1905, 1906 is very different because they did traditional wet chemical determinations of major and minor ions. After established technology, this was developed at the late 1800s, and they used, of course, much larger volumes, 1/2 liter. And the process is kind of involved. When I was a student back in Göttingen, we learned to do this, and you can, if you're careful, you can be very good at determining concentrations this way. So what you do is you're dissolving and drying your sample. You're driving off the silicate, and you're determining the silicate contribution by difference in weight. Then you're doing a colorimetric determination of iron after precipitating this. And then you're splitting your filtrate into 2 sections. One you're using to determine calcium oxide and magnesium oxide by titration in some chemical form, endpoint titration. And The other part is being utilized to precipitate sulfates to determine barium concentrations. And the residue is then used to precipitate potassium oxide and sodium oxide as chlorides. And this is where this combined potassium-sodium analysis comes from. It's just a way, fallout of the way these samples were processed as potassium and sodium chlorides. The error introduced by not separating sodium from potassium is actually quite small, but it depends on of course, the percentage that the potassium makes up in this combined sum. And I'm going to dive into that a little bit later to just constrain the uncertainties we are introducing by treating these chemicals the same. If you look at the molar masses, they're quite different. So depending on whether potassium chloride is 10% of the total or 20%, it can make a difference of a few percent. But in my estimation, it's less than a 10% uncertainty that is introduced by combining them. What I also want to let you know is that this year, 1905, 1906 was not abnormal at all. So if you look at the long-term record of discharge in the Mississippi River, these are 1905, 1906. So they were elevated, but not outrageous, unusual in any sense. So in that sense, it's like a normal year we encounter in the last decades as well. All right, now let's plot this relative contribution of sodium relative to the sum of sodium and potassium to discharge. And what we find here, that there is a correlation with discharge. So in high discharge years, the contribution of potassium to the combined sum is larger. In low discharge years, it's really dominantly sodium. So less than 10% is then made up of potassium. And in 1905, 1906, that is indicated here by the red triangle, we have about a 15% contribution of potassium on average. I mean, there's quite some scatter here, but 15% is sort of a good estimate. So based on that, I would say that by combining sodium and potassium in a single analysis, we are probably making about a 5 to 7% uncertainty. We are introducing uncertainty on that order of magnitude. So this is the 1905, 1906 data. These are the weekly averages. And this point here, the blue point, is the overall weighted average, weighted by concentration and by discharge for this entire data set. Now, Mr. Stone, who was so instrumental in getting this time series started in 1905 for a year, he actually took one sample and processed it further. And I'm going to come back to that in a minute. I just want to show you where the weekly averages for this 1905, 1906 record fall in relationship to the records I showed you before. So in red again is our record from 2015, 2016. In yellow is the 2003, 2004 record, also from New Orleans. In black is the record from St. Francisville. And then in blue is this very old record over 100 years ago from 1905, 1906 with the weighted average. So you can already get a sense that this record is slightly different in composition compared to the more modern records. All right, I'm doing two things here now. First, I'm just taking the modern records and I'm artificially combining sodium and potassium, much like these early records from 1905 and 1906 were compiled, just to have a direct comparison without trying to separate the sodium and potassium. So this is what these records look like. Again, our record from 2015-16, the record from 2003-2004, and then the longer term St. Francis Law record from the USGS, plotted on top of the weekly averages with the weighted average from 1905-1906. Again, you see on average, these blue data points are shifted slightly over to the right, maybe slightly shifted up towards the upper left corner of the diagram. So let's dig into that a little more. These were the conditions at the day of the sampling on May 23rd, 1905, the only sample of this record where sodium and potassium were actually separated and analyzed separately. And this was done by refining this step here and separating potassium and sodium, actually having an alcohol-soluble potassium platinum chloride that you can separate and then weigh independently of the sodium chloride. If you do that, the value now in the magnesium sodium, calcium sodium diagram plots right here. So right in the overall trend of the data, and certainly somewhat distinct, but not outrageously different from records of the modern. Yeah, this gives me confidence that the chemists who worked on this 115 years ago did a really good job doing these wet chemical gravimetric determinations of element concentrations. All right, so this is what I really want to show you. This is the magnesium sodium, calcium sodium plot of the modern trend from 1965 to today, with these back and forth in composition depending on drought years versus flood years, the overall shift towards more magnesium-rich composition, and compared to 1905, this is the annual average of 1905, a significantly different composition. So since over the last 115 years, the composition in major ions of the Mississippi seems to have shifted towards more sodium-rich compositions and more magnesium-rich compositions. Why is that? All right, let's look at the contributions from the various tributaries, because it could simply be a shift in the contributions from any of these tributaries. So the most variable of them is the upper Mississippi. This is one data point, another data point, another, and another. Tremendously different. So a lot of variability in the upper Mississippi. We actually do have data for the upper Mississippi in that Clark paper from 1924, which is really amazing. So these are samples from the upper Mississippi that span almost the same range in chemical composition as the modern record. So I don't think it is related to a change in the chemistry of the upper Mississippi. And it's also not a change in the contribution. I'm not going to go into that, but we have stable water isotope data that confirm that. All right, what about other contributions from other tributaries? You remember, this is the Ohio, this is the Arkansas, and then the Red River down here. So the Red River is an interesting case because in the old days, the course of the Mississippi ran differently than it runs today. There was, back in the 1500s, a bend in the river that connected the Red River to the lower Mississippi River as it is today. And even in 1831, the turn of the river went like this red line here, which is called the Turnbull's Bend. And then an enterprising river captain decided to cut across this bend to eliminate transport around this bend and cut down on shipping costs. So Mr. Shreve, he cut the river right here, essentially widened the channel, dug the channel, deepened it here, and connected the Mississippi to the lower Mississippi, essentially abandoning this bend. The only remaining connection is what is now known as the Old River, which is in theory a connection of the Red River into the Mississippi, but the flow goes the other way. So mostly it's a flow of the Mississippi River into the Atchafalaya distributary. So the Red River today flows directly into the Atchafalaya River. So there's no contribution from the Red River directly into this part of the Mississippi, which represents both the St. Francisville data set and our data set in New Orleans. New Orleans is farther down south following this eastern bend of the Mississippi River. So since 1831, the Red River has essentially been disconnected from the Mississippi, the main Mississippi, which means that our records cannot have been affected by the Red River itself and changes in its composition. So we can disregard contributions, changing contributions from the Red River, meaning that we can't argue that from 1905-6, which is this data point, to the modern is driven by increased concentrations from the Red River, which in a binary mixing you could argue. So we have to look elsewhere, how the river moved from this composition to this composition, more sodium rich, and over the last decades, more magnesium rich. Of course, this is not a pristine basin anymore. This is the evolution of the population of the United States since independence. You can see the scale here in millions, starting from very low numbers to now almost 330 million. Just to give you a sense of where we are, this is when we started our time series. This is when the USGS started the time series in St. Francisville. And this is when this record, 1905, 1906, is taken in New Orleans. So clearly over the last 115 years, the basin has become more populous, more industrialized, and more intensely agriculturally used. Another record that is also interesting to compare is the almost extinction of the beaver population. This is plotted on the same axis in millions. So this is the North American beaver population in millions. So you can see our forefathers have decreased an amazing population of natural river engineers to near extinction. And with that triggered a significant change in the hydrology of the basin. Another change is the deforestation. This is the axis here on the right-hand side from 0, 50% to 100% forest cover. So this was essentially a forested basin, which was deforested in the 1800s and 1900s to a now relatively stable level of about 60% forested. So again, significant changes in the landscape evolution that not only affected water chemistry, but likely also affected significantly the sediment transport. And then of course, and you know this is a time series reconstruction of dam building. The annual counter is up here in the upper right, upper left. So we are at almost 1900. You can see that the dam building starts here, but it doesn't really take off after the first 1905-1906 record has been established. Yeah, so now, today, the Mississippi River Basin is intensely modified by dam building. And this can affect the water chemistry. We know that for sure, and it definitely has affected the sediment transport. You can see at the time of the first record, 1905, 1906, there were just a few dams in the basin, very different to what the situation is now. All right, where could this change in water chemistry come from? Let's look at road management, both in the wintertime. Putting salt on the roads can certainly have an effect. So let's try to quantify that. There's also fertilizer, potash containing potassium and sodium, liming, adding calcium to the fields, and then tiling, so artificial draining. There's water treatment mandated in all of the communities now. Just to give you a sense of my own hometown, we have a water treatment facility where polyaluminum chloride is being used. So chlorine is added, and then sodium hydroxide is also added to control the pH. So clearly addition of sodium, but also precipitation of salts and modification of the water chemistry as a result of that water treatment that can affect primarily sodium, but also calcium and magnesium composition. So what I've done is I've dug into the records of salt use in the Mississippi River Basin over time, and I've computed what the addition of salt could have added to the chemistry of the Mississippi River. This is now on this axis here in milligrams per liter, the potential addition of sodium in these brown dots and chlorine in green over time. So you can see that the salt use overall has, of course, increased, and with it, the potential to increase sodium and chlorine concentration in the river, because these chemicals don't stick around in the landscape, they're easily soluble. If we do that and add this anthropogenic salt use to the composition of the river in 1905, 1906, we get this theoretical composition here. This is still different from the actually measured composition up here, connected by the black line. So this is the real Mississippi. This is the hypothesized Mississippi if we started with the kind of pristine composition in 1905, 1906, and simply added what would have been added by the modern salt use over the decades. So we can't quite get there. There's still an excess of sodium that we are observing in the modern river. So anthropogenic salt use cannot be the sole reason. We do the same for chlorine, again, starting with the chlorine concentrations, 1905, 1906. You can see the chlorine concentration goes up, but it doesn't reach the observed concentration. So there's still an excess of chlorine. So again, salt use alone can explain it. It may explain about half of the observed increase, but not more. What about other potentials? So this is an iconic opening scene, once upon a time in the West, famous Western. You can see in the background the water tank here that is crucial for driving the railroad. And what you can also see is a pumping well here. So even back in the 1860s, groundwater pumping in the West was an important source for groundwater and surface water. And over the year, groundwater pumping has depleted these aquifers, particularly in the high plains, quite significantly. This is a trend of depletion from the 30s to today. And what you can see is the southern high plains aquifer, the central high plains, and the northern high plains. Very little change in the north, some change by about a third in the central high plains. But the southern high plains aquifer has been decreased by half. This is continuing, so it's more than half now. If you look at the overall United States groundwater pumping, that's the black line here, the high plains aquifer account for about half of the total US groundwater usage. And this is almost equivalent to a year's worth of the flow of the Mississippi River combined in aggregate. So it's a very significant contribution. Interestingly, the composition of the high plains aquifer, particularly the southern high plains, are plotting towards this more sodium-rich end member. Compare that to the northern high plains, they are sitting right here. So clearly the southern high plains, the aquifer that has been depleted the most, have the chemical composition capable of driving the Mississippi River composition towards that more sodium-rich end member. And I think that groundwater pumping certainly has the potential to explain the increase in sodium and probably chlorine as well. Because again, these are soluble salts that end up in the distributary system. But while this may explain the trend towards higher sodium concentrations, we still have to find an explanation for this apparent increase in magnesium concentration that is overlain on this overall trend. So there, it is interesting to look at what happens during the summertime. Many of these unpaved roads, dusty kind of dirt roads, are being treated in the summertime to reduce dusting. And the chemicals used for that are somewhat analogous to wintertime treatment, but there are also hygroscopic chemical treatments that involve magnesium chloride, calcium magnesium acetate, and potassium acetate. And these are just sprayed on the roadways. They bind the dust, keep the little moisture that's available on that road surface, and prevent dust plumes from emerging from the roads. So this is another artificial human-induced alteration of the chemistry that ultimately affects the surface runoff. So I'm thinking that the combined effects of water treatment and road management plus corrosion control, this is something that has been introduced since about the 1940s, 50s, where active corrosion control, mainly using magnesium metal underground to protect infrastructure, particularly water infrastructure, pipes, but also natural oil and gas pipelines, and any underground installation you may have that involves metal tanks or metal piping. Corrosion control using magnesium metal is quite common. So this could also contribute to driving the composition of the Mississippi River towards its modern observed composition. So overall, I think those are the main drivers: salt use, groundwater pumping, road management, and corrosion control. And then this overall trend is overprinted by the annual hydrologic changes in the basin that have the flood years plot towards the more limestone-dominated composition, whereas the drought years are less dominated by limestone contributions. So with that, I'd like to open up for questions, comments, answers. This is a research project that has kept me busy for a number of years. I haven't quite finished it. I'm still looking for old records, but I think I have a much better understanding of how and why the river chemistry of the Mississippi River has changed the way we've observed it. So thank you for for attending the talk, and I'm interested in Q&A.
So Bernhard, thank you very much. This is amazing. You have that data set. You know, we are able to see the time series of change. I'm very interested. I mean, the course you proposed, particularly road management or water treatment. If this is true, there could be many other river systems should show a similarly trend of change, because, you know, for example, the salt they put on the road in the winter, and definitely somehow will discharge to the river. And do you see any other system show a similar or some kind of, you know, trend?
I have not looked Paul. I know that there are other river records, particularly in Europe. For the large European rivers, there are actually quite good records available for the Thames in England. I think the Loire has pretty good records. The Rhine has very good records. The Danube to some extent. So there, and those records go back to probably at least the time we have records for the Mississippi. And they are also very heavily industrialized, but I have not dug into these records in greater detail.
Wow. You should get a couple students, or we have could we have a international work group. That will be interesting. Look at the global water chemistry,
Right, and in the developing countries, if we look, for instance, China, since the 60s, the amazing industrialization of that country, we know that it had an effect on the river chemistry. And I know that there are records out there. I have not dug deeply into that.
Okay, we have a couple times colleague like Shu Ye from Shanghai. I think he may be the good person to work with.
Mm-hmm.
There are Shu Ye? Oh, I'm sorry. Let me. Okay. Yes. Now, Christoph. Yeah. Shu Ye. Yeah. Oh, Christoph.
You hear me?
Yeah, yes, now, sorry.
Yeah, okay. Yeah, it's very, very impressive talk, a lot of data, yeah. Yeah, I cannot imagine in China we can, extend the data from Changjiang to the early, yeah.
Yeah, I think even a decade, if not that extend that long in terms of chemistry. I know China keep a good water and sediment data, but the chemistry, I'm not sure. The Shu Ye, you can dig in a little bit. You do a comparison of Yangtze and the Mississippi, that will be great.
Yeah, probably, yeah, that quality is a problem, I guess, yeah.
Yeah, but if you get a couple years data, it's worth to take a look, okay?
Yeah, may I have a question?
Yeah, let's Christoph read the hand first, you Shu Ye. So you are the second, okay, Christoph.
Sorry, Shu Ye, you'll have the floor afterwards. Just one question. Some years ago, there was a paper by I think that was Peter Raymond that published a paper with a long-term record of alkalinity. I think it
exactly.
was that he showed us like books that were stored like in a in a lab that was surveying the water quality of the. So how does and I don't I recall that it was like linked to the alkalinity increase was linked to the lime that people use in the fields in the watershed. So how does that relate to? Did you take that into account in your analysis yourself?
Yeah, that's an amazing record from the New Orleans Water Board. They have these alkalinity titrations for over 100 years, and that's the record that Pete dug into. And you're right, the initial paper made this observation that the increase in the alkalinity is linked, according to his interpretation, to liming, but also tiling, so the more efficient draining of agricultural fields, particularly in the northern central part, the breadbasket of the United States. There's a later revision of that to some extent because it turned out that the hydrology also plays a significant role. It's a slightly shorter record, and over the duration of that record, there was an increase in water flux as well. So it's sort of a combined effect of more runoff and a different composition because of anthropogenic modifications. Both the liming, the tiling, the difference in land use. I have not fully quantified the liming records because I have not found a good source of data for the entire Mississippi Basin to be quantitative in that. But you're right, what I could do is I could go back and reverse engineer the data, essentially invert the alkalinity data. And if it is linked to liming, essentially argue that there's a relationship between calcium and alkalinity that allows me to quantify those contributions. Mm-hmm. The thing is, though, that would drive the record in the wrong direction. That would make it more calcium rich, whereas I'm observing exactly the opposite.
Yeah,
so
it's more like
trend would have to be compensated by other trends or overcompensated.
Well, it's interesting. Okay.
Okay, so yeah.
Oh, okay. So, Bernhard, yeah, again, I thank you very much for presenting so impressive talk. I have a small question. You showed some change in these element ratios. You mentioned probably the anthropogenic input is a major cause. I wonder. Also, you mentioned the global warming. So I wonder whether chemical wearing plays some roles.
Yeah, so clearly global warming affects the Mississippi River basin primarily in its hydrology. We see a trend towards increasing runoff. And I showed you the correlations of the elemental ratios with runoff. There's a clear correlation there, but the correlations are such that they cannot fully explain the observations because they go, in the ratios that I looked at, they vary in the same way. So they tend to increase with increasing runoff, whereas the observed water chemistry doesn't quite follow the same trend. So it's not just the global warming and the change in hydrology that can explain this. There is an anthropogenic contribution, a direct contribution, so not indirect by global warming, but direct contribution by adding chemicals to the watershed.
Okay. Okay, but I also, see some amplitudes. I mean, in variations of these two element ratios, calcium to sodium and manganese to sodium. Yeah, we can see the trend, very good trend, but we also see the, uncertainty or variations. So
Absolutely.
what's the meaning of that? Yeah.
Yeah, there's obviously a lot of variability on an annual basis, as you see here, and this can be quite dramatic. I mean, if you look at consecutive years, this is 81, this is 83. So this is clearly driven by hydrology. This is not probably not direct addition of anthropogenic chemical contributions. 81 to 83. So this, I believe this high resolution, high frequency pattern is entirely driven by hydrology. But on a larger scale, these variations are noticeable, but relatively minor compared to the overall trend.
Okay. So another small question. The last picture you show is very interesting. So what's the reason for the, frequent shift of this meanders? Yeah.
Yeah. So this is this famous reconstruction of Mississippi meanders.
Is it also anthropogenic?
No. This is almost entirely natural. There may be some cutting across, in certain areas where, we, society, have engineered the river. But mostly these are longer term records over the last couple of hundreds, maybe even thousands of years of the routing of water and sediment by the Mississippi River to the coast.
Yeah. One factor to remember, the Mississippi River, the height of water only a couple 100 meters. And so overall, the gradient of the Mississippi is very, very low. Compare other large river systems like Amazon. Amazon is a couple 1,000 meters, Yangtze, Changjiang, any other river. So Mississippi River relatively is flat you know, so this is the other factor. So contributed so much meandered, so much that kind of channel change, maybe. Yeah. But okay, I see the Yijun, yeah, from Louisiana. Hi. Okay, Yijun, go ahead.
Hi, Bernhard, thank you for your talk. I have a quick question about your data collected by the Tulane University in 2015 and 16. Do you have also sediment data for these 2 years?
No, we don't. Unfortunately not. You know, we did not sample from that floating dock because we knew that if we did it, it would be a very biased record. You know, in order to sample sediment flux in the Mississippi River, you have to do it right. So Mead Allison, you know, he gave this wonderful talk in this series a couple of weeks ago, where he showed how spatially variable sediment transport can be, and what you really have to do in order to capture that. So we would have to do ADCP transects across the river and then sample probably depth specific or depth integrative across the channel, and we have not done that. You know, that would have been a major investment in time and money, and we just didn't have those resources.
Okay, so do you remember what filter size did you use or was used to filter water sample?
Yeah, so this was all 0.22 micron filtration. So of course we have the filters that we used, you know, we have those preserved, but that's a very biased, very you know, representative of a single location in the river, right at that floating dock, and dominated by the surface. There's also a significant change in chemistry, particle chemistry, from the surface to the depth. And if you don't sample those gradients properly, you get a very biased chemical composition.
Okay, so maybe just something, and I think maybe one could analyze the data separated by hydrograph. And I'm thinking, you know, you analyze your data on the rising nymph. So when flood comes, and versus falling nymph. So on a hydrograph, you know, on a hydrograph you have when floods coming. So you separate your intensive data and exactly. So you analyze data on the rising nymph and versus falling nymph.
Yeah, we can do that.
Yeah, maybe that way you could figure out, because we have a pretty good idea about the sediment pattern of the falling and the rising. So sediment tends to be higher on the rising nymph and much lower on the falling nymph. So maybe you just something I'm thinking about.
Yeah, that's a great point. I mean, that's something we can easily do. You know, yeah, that's clearly something we can do.
Yeah, and we have some data. We analyzed actually a lot of data on rising and falling. So we know their dynamics and the suspended particles and also sand particles. So just some thought. But thank you. Good to see you. Good to see you.
Thank you.
Yeah, Bernhard, I have a last question. You know, many major rivers, including Mississippi River, Yangtze, Mekong, Nile, so the sediment sharply decreased up to, you know, 80 or 90% compared 1950, 60. So correspondingly, sediment concentration is decreasing, because most of river, the water discharge still keep a consistent relatively. So the sediment concentration will affect the water chemistry discharge to the ocean. I don't know. So what's your opinion? Because you look at the global river observation. What your sense?
Yeah, it's funny. It's funny, Paul. And this is a point of a lot of contention. There's not a lot of great data available to speak to that problem. And it's because you have to separate the contributions from the particles suspended in water during transport from contributions in the floodplain, particles in the floodplain interacting with groundwater, contributing to the river.
That's true.
We know that that contribution is significant. So in that sense, chemicals, sediment particles in the floodplain contribute significantly to the river chemistry. And that has been shown in quite a number of rivers. The prime example I can recall is on the Ganges, where for some of the major ions, it's a really significant contribution.
Yeah.
The contribution from the particles floating in the water, that is much more difficult to discern. We have, and anecdotally, there are accidents that happen. There's one, my colleague Valier Gali, he tells me the story that his brother forgot to filter a sample for a couple of months. And so he sampled the sample after a couple of months, so separated the water from the particles after a significant delay, but the water chemistry was not apparently not affected by it.
Oh, interesting.
We have done some experiments both on the Ganges and the Amazon, where we suspended particles in filtered Amazon and filtered Ganges water and analyzed the water chemistry during those experiments. And you can see changes. So there's certainly the potential that particles, as they are being transported by the river, can affect water chemistry. But I think it's a minor effect.
Oh, okay. That's interesting. Sometimes even the dam impact can trap the sediment, but not really trap the chemical.
Absolutely.
Somehow. Anyway, that's I think when it's always true when we open one box and we have more unknown ahead of us. So we think we solved the problem, but actually there's more problem ahead of us. So it is great. This is the life of academia. So thank you, Bernhard. Thank you very much, and it's a great talk. So I see you guys.